Yes, class. Rajata, you weren't there in the optics class. Rajata,
No, ma'am, I was there.
you were there. Deborah, you were
Yes,
there.
ma'am.
Deborah,
Yes, ma'am.
you were there. Sidra was there. Amna was also there, I remember. Yes, Mir Hussain, were you there? Okay, let's start with the class. See, let's complete EMI. So mutual induction we had to start now. All right. Mutual induction, see, same thing that is occurring in self-induction. In self-induction, what happened? In self-induction, you had a coil in which there were changes occurring. Either the magnetic field Mir Hussain has left. As soon as you call his name, he keeps on leaving the meeting. See, when there is an increase or decrease in the flux in one coil, and that produces the induced EMF effect in the same coil, we call it as self-induction. Same thing over here, it's just that you have the primary coil here, you have the secondary coil here. Between them, mutual induction will occur. Changes, flux will increase or flux will decrease in the primary coil, and induced EMF and induced current, these things will occur in the second coil, that is known as mutual induction. So it is the phenomena of production of induced EMF in one coil due to change of current in the neighboring coil. Phi is directly proportional. Now similar, everything is similar. You can notice this that there also flux was directly proportional to amount of current in self-induction. Here also flux is directly proportional to the amount of current. What is the difference? There it was self-induction, same coil was there, so coefficient of self-induction, which was self-inductance, was used, L. Here we are talking about mutual induction. Two coils are present. One is bringing the change, in one the change is being produced. So the coefficient is coefficient of mutual induction, or you call this simply as the mutual inductance. Self-inductance and mutual inductance, these are the two common terms which are used. Rather than using a coefficient of mutual induction, coefficient of this and that, it's better directly use self-inductance. Both have the same unit Henry. Both have. And formula is also same. See, phi is equal to Li was the formula. Here the formula is phi is equal to Mi. All right, so similarly, the way you have E is equal to minus LDI over dt, you have here E is equal to minus MDI over dt. All these things are same over here. SI unit here is Henry. All right. And one more thing. If you're saying SI unit is Henry, you should know that mutual induction is EMF DI over dt. This you should be aware of. This is DI over dt. So when you're defining 1 Henry, you should write 1 volt by 1 ampere per 1 second per second. So volt second by ampere, this is equal to 1 Henry. You should be able to define what is 1 Henry. Now mutual induction between two coils are left. To define mutual induction between two coils, two long solenoids. So when you had a single coil, it was very easy to write. V is equal to mu naught Ni, one formula could be used, and we had seen that derivation also. Do one thing, write down the above part, then we'll start with this. Write down first about mutual induction, start with it, then we'll do for the long coil. So see, these are the two wires. One is having current I1, number of turns N1, but the similarity is that both of them have the same length. Now see, when I talk about the flux generated by the first one, so magnetic field will be of the second one. Rest of the things will be the same, area and N1. Phi is equal to BA. Here number of turns are mentioned. So we'll multiply it by the number of turns. So this is it. When we write magnetic field for the second one, because we have to find out the value of B2. So B2 can be written as mu naught N2I2. Why? Because the formula for magnetic field of a solenoid is B is equal to mu naught Ni. This is the formula, right? Now see what will be phi if you put in this value. Mu naught N2I2 AN1. So mutual induction of first with respect to second. We know it's phi is equal to mi. So m will be phi divided by current. So what is the value of phi? Mu naught N2 I2 A N1 divided by I2. Current gets cancelled. M12 becomes equal to mu naught N2 N1 divided by L. Fine. This is the formula. And similarly, if you want to find out the vice versa, phi 2, when you have to find out for phi 2, we'll write it for B1, mu naught N1 I1. Phi 2, we will write B1 A N2. This time it would be B1 for phi 2. The second one is taking the magnetic field of the first one. So phi 2 will be equal to mu naught N1 I1 A into N2. Same thing. So M21 will be equal to, now you can calculate this by yourself. This is mu naught N1 into N2 into area by length. So what can we conclude? What the question can come? You have to prove sometimes M12 is equal to M21. So these are the calculations which you have to show. This can be asked to you in this form. All right. You have coefficient of coupling also. One thing before this. In the area, pi r square is the area. Accordingly, whichever coil is asked, R1, R2, you can substitute and calculate. Okay, coefficient of coupling is just a formula which you have to remember. It's a coefficient which acts between the two wires whose formula is mutual inductance divided by under root of L1 into L2. What is meant by this is that, see, suppose this is one coil, this is second coil. All right, just understand this is very easy. You will be able to relate it. This coil, both of these coils are having mutual induction because these are two coils. So they'll be having mutual induction between them. Fine. That's why we have this M in our system. But see, these are individual coils also, no? By themselves, they are individual coils also which are existing. So if they are individual coils, they will also have self-induction going on within them. So L1 will also come into action and L2 also. So in order to relate all these three, we have a coefficient which we call as coefficient of coupling, whose value is usually between 0 to 5, I think. I just have to confirm this. I don't remember. So K is equal to M divided by under root L1 into L2. All right. Write down this. Then we'll start with alternating current. Done, class. Just text me done in the chat column, then I'll start with AC. Yes, class. Now chapter 7, alternating current. So alternating current, before alternating current, till now, which current we were talking about, it was the direct current. What is meant by direct current? Direct current means with respect to time, it is not changing. Like in the questions till now, which we have studied, did we ever use the term that current in the first second is 5 amperes, in the last second is 10 amperes, then in the middle it has decreased and it became 0? Nothing. We haven't used. In every question that we have solved till now, we have just said that current is given as 2 amperes. That's it. Because direct current means time is continuously increasing. See, time is a parameter that is not in our control. Time will always increase. Time can never decrease. Time can never be 0. Time will always increase. But second parameter, that is current, that we can assess. So current is increasing. See, suppose this is initially 2 seconds, current is this much. Then 4 seconds, current is still only this much. Time is increasing, but see, the value of current is still the same. This is not decreasing. This is constant, the value of current. So this is direct current. But when we talk about alternating current, in alternating current, we have variations of current. You have the variations of current. You will see current is increasing, then it's decreasing. It is depending upon time. It is depending upon angular frequency. It's depending upon the distance. So many parameters are there which will determine the current. All right. So alternating current is there. Alternating current means the current is changing with respect to time. All right. It's changing with respect to time. So for example, this is the best way to represent this. This is the origin. Why? Because the current varies sinusoidally. Sinusoidally means this is a sine curve. This is a sine curve which you get. Sine, cosine also we have, mainly sine curve which we have. This type of graph you will be seeing a lot. This type of graph. All right. Okay, AC generator, AC dynamo. It's a device that converts, basically you have mechanical energy. What is mechanical energy? Mechanical energy is the sum of kinetic and potential energy. This is mechanical energy. which is the sum of kinetic and potential energy. This gets converted into the electrical energy. This is the basic mechanism behind the AC dynamo AC generator. In your NCRTs, you will find this topic in EMI only. I am doing it in AC because this is actually a part of AC. You are talking about every term. You're talking about all the terms which are present in with respect to alternating current. That's why. Okay, principle Faraday's laws of EMI. That's why this is actually a part of EMI. You will be seeing magnetic fluxes getting involved, everything which you have studied in EMI. It's actually a part of EMI in your curriculum. We do it, we started with we include in this lesson over here because the parameters that are present, you will see further. Those are a part of alternating current only, and that initiate this. All right, so it is based on Faraday's laws of EMI. Whenever flux will change, EMF will get induced in the coil. Basic Faraday's laws of EMI is equal to minus d phi over dt. In an AC dynamo, magnetic flux gets changed due to the motion of the coil in uniform magnetic field. Till construction, let us see. Then we'll see the calculation part in one go. Basically, you have two magnets, north and south polarity. In between, you have a coil, a rotating coil. This coil rotates with certain angular frequency and angular velocity, omega or nu. Permanent bar magnets are kept, and they are kept in a manner where normally magnetic field will be projected on them. All right. And to just insert the coil, there is an armature on which two slips are present. And these two slips, they are continuously held when they are rotating. Now, basically, we'll involve magnetic flux that I'll tell later. First, write down all these points. See, number of turns, this is N, area is A, B is magnetic field, W is the angular velocity. So phi is what? Phi is NBA cos theta. Flux is, magnetic flux is BA. If number of turns are there, we'll multiply it with N, and B dot A is there. So when you will expand, cos theta will also come. So that's what I was trying to tell you. This depends upon angular velocity. How? If you remember, do you all remember this relation? Omega is equal to theta by T. In class 11th, you must have done this. Rate of change of angular velocity is equal to rate of angular velocity is equal to rate of change of angular displacement. That is theta divided by T. All right. Yes or no? Do you know this or not?
Yes, ma'am.
Okay. Anyway, this is easy. All those who have forgotten, like you have linear velocity is equal to linear displacement by time. Similarly, this is angular velocity equal to angular displacement by time. So from here, we can have the value theta is equal to omega t. So equation becomes NBA cos omega t. Now you can see flux is depending upon omega also. It is depending upon time also. But what about EMF? Our concern was with EMF. So we have this relation E is equal to minus d phi over dt. Now substitute in there. This becomes NBA cos omega t divided by dt over dt. So when you will differentiate this, this should become, this is sine omega t. This will become omega cos omega t. Always remember this. And when you are differentiating this sine omega t, you're differentiating this will give you plus cos omega t. And when you are differentiating cos omega t, this will give you minus omega sine omega t. Remember this? This is helpful for the entire lesson, not just this portion. Now see, when you will differentiate cos omega t will give you minus omega sine omega t. This will give you minus omega sine omega t, this part. And rest NBA minus, this is already there. So this minus into minus, EMF becomes NBA omega sine omega t. All right. See, one thing class, sine omega t. What is this? It's like sine theta only. We write sine theta. This theta part is replaced by omega t because we have intentionally put this. Earlier it wasn't like this. We have intentionally put this. So sine theta is equal to omega t. So if sine omega t is 1, means omega t is equal to 90 degree. So the maximum value of this EMF which you can achieve, the maximum value, it can be NBA omega only. Because cos omega t part, sin omega t part 1 will become 1. So NBA omega. One thing class, this maximum value, sometimes we call this as peak value also, that I'll discuss it. So you have formula I naught sin omega t. I naught means this, all these entire maximum value term. Similarly, E will be E naught sin omega t. This you will see later also. So how will you have the graph defined? EMF is increasing. A maximum value has been achieved, that is NBA omega. Then again, it's sinusoidally decreasing. Then it is becoming negative. Sine curve you are obtaining. So this one entire duration, when this going, this one entire duration, that gives you one time period of a graph. And this entire separation, this is one wavelength. Fine task. Tell me first one thing. Is it clear till here? Fadil? Fadil, you there? Okay, Fadil. Sidra, Deborah, clear? Because this is the initial part, it's easy. This is easy. Okay, write it down. Good. Any doubts if you have, you can ask me in between. All right, class, tomorrow I'll continue this lesson. Just revise the concept of magnetic flux. Rest of the topics are new, so that I'll discuss it tomorrow. Okay, you all can leave, all those who have completed. Thank you so much. Tomorrow we'll continue.